Okay, next, I'm very pleased to introduce our speaker today, Carlos. And then let me just tell you a little bit about his background. Carlos Arimbar is a data scientist. He loves to learn, actively participates in multiple meetups, and enjoys discussing new developments in tech, software, and data. He is also a volunteer for Postgres SQL. And also, I just forgot, but we're also being hosted today by DPI. And I also wanted to hand it off to our DPI representative today just to give a few words about what DPI is. So if you want to come on up.
Yeah, hi everyone. This is Anuj Tiwari. I'm a senior research associate at Discovery Partners Institute. I'm here to participate in the PyData as a user. But besides that, I love to introduce DPI. DPI is a part of the University of Illinois system, conducts tech workforce development, applied R&D, and business building in Chicago. It is one of the 15 Illinois innovation hubs, network hubs, each of which is associated with one or more than 12-year public universities in Illinois. DPI goal is to attract world-class tech talent to Chicago for tech careers, and to facilitate corporate investment in Illinois, primarily through training and education and through applied R&D and business building. And we love to host PyData today here and also Carlos. So, so thank you for being here. Yeah.
Let me know if everyone can hear and if everyone online can also check that everyone can hear. That would be great. So today I want to talk about like neuroimaging analysis. I know it's a topic that a lot of people don't have to deal with it until like it comes up or for your own sake. So that's why I actually got the interest for myself. Kind of like a little bit myself again. I usually have like a background. My name is Carlos Ranibar, and I have more like a background in economic statistics. And as I was mentioning to Olivia, I actually pivoted more from chemical engineer during undergrad to statistics and econ because I already knew I like working with data, and like computer science. That was easy to transfer, and as well like all the software you can learn it as you go, as I have done with pretty much all my roles, because we use different software for every single one of them. I'm a data scientist. I did also a master's, and I work with different industries. I have worked with manufacturing, more like consumer goods, foreign exchange, and I'm working with healthcare, which kind of took the lead to this talk. Also, a shameless plug that we actually wanted to bring up for everyone for a different reason is like, as I mentioned, a volunteer for PostgreSQL. They're actually having a PG Day on April 24th here in Chicago. And with that one, it's a one-day conference and still like looking to add sponsors. And the reason I mentioned is like even for PyData, it doesn't cost money if you're a community. So if PyData want to be sponsored with it, it actually doesn't cost. So not just that, but also any conference or if people want to attend. They also have like a coupon that they gave for the Postgres user that it was like I think $25 off. They gave only 25 of those early this week, so I'm not sure how many we still have left. But if you can still take advantage of it, they have it in New York, and this is the only one. They had it last year, and the US only has these two, versus Europe has so many of them. And even though if you don't use PostgreSQL, a lot of the content is transferable from the actual talks, since they have like 3 at the same time. So if you use any query languages, I'm sure at least one of the talks will be helpful for you. So that kind of brings us to the topic of today. So there is like a couple different reasons to study the brain. The most common ones is like MRI and EEG. There's also some rare uses of CT. And the reason why the different approaches, MRI is more for the actual brain. It could be for interaction, but also for the way that if there's any damage to the actual brain, as well as like the internal brain that we can't see because it's an organ that we can only watch but not touch as much as others. So that's why it makes it challenging to actually study what's going on. So I'm mentioning these studies, but the one I'm focusing most is actually EEG. EEG, it's an electroencephalogram, which means electro comes from electricity, encephalo, which is the brain, and gram is from writing. So it's pretty much writing the brain electrical activity, which with that, what happens, it's pretty much measuring the activity brain, the electrical activity of the brain. And how it happens, it's more finding the differences. So you put the diode, which is the electrode here, and it measures the difference from one to another. So you kind of, the typical kids book that you have, like spot the 7 differences. The only things that will show in the graph are the different current activity that goes on. I'm not sure, I'm sure it's not the most common study that anyone has seen, but something that is more popular is the AKG. Is a typical graph of the heart rate. They do the 12 lead, I think usually within a health checkup. And as well as if you are doing like, if you haven't ever done it either, like it's a typical graph that you see during the movies when you have like a patient in bed, like the heart rate is pumping, and when it goes flat, you don't want that to happen. Similar with the brain, that's even worse. So the benefits of the EEG, this is actually a device that is like kind of like a hat looking. Usually the way they do it, they attach the electrodes to your scalp. It's like a surface and non-intrusive method to measuring the brain activity. The way that this one happens is there is the different diodes, and it helps to find like detecting epilepsy, brain disorders, monitor sleep, and brain function in general. So it helps to see at what state your brain is. I know like lately there's been a lot of more like performance or your brain activity of being on alpha state or different frequencies. This is one of the best ways to measure it. It's still like on the surface level of the scalp. So if there is activity that goes very in deep into the brain, it would not be the best to pick it up, but that's like also very hard to measure in any other method. So this is still the best way to approach it. And the reason how it works, it's called the 10-20 system. The reason why we will showcase this, why this matters, is more the naming convention of it. So we can see the 10-20 system. The actually bottom left graph is better. So we can see the different parts of the brain, like the frontal. So if we see on the left image, is called like FP1, so it's frontal, and then the P is on the left side for the odd number, and on the right side for the even numbers. And also if it has the letter Z, C, it's like for 0, so it's like on the middle line. So I know I'm kind of covering a lot of different and like medical terms for it. So let me know if there is any questions that might come up as well. So I know I'm kind of just ramble a bunch of like medical terms and like the study of why I approach it this way. So the reason kind of why I came up with this, it's more within the brain activity itself. So I actually got a device, it's called a Muse. I'm not sure if anyone has heard of it before. It's initially intended for meditation. There is actually different versions. This is called the Muse S, and I am not sponsored by them by any means. I got this more for fun. Like I like the devices that measure activity. Like I have like the Garmin or the Oura Ring, more for my own traceability. And it's called Muse S because this one's at least aimed for sleeping. Even though I actually tried a couple times, and I feel like the Oura Ring is equally as good about measuring the sleep, even though it's like a way more portable and easier to wear a device while sleeping versus like an actual headband. But the point of the actual Muse initially was intended for meditation. I think it's a great approach for the sake. If we have a comment on the chat, I'm not sure. I haven't seen it. Do you wanna? Okay, sure. No worries. So it's intended to like help people meditate. I can actually showcase kind of how it looks. The application is like super user friendly. But that's. So the device kind of looks like this, and the way why everything else matters, like before we have the 23 electrodes, this one only has 6, which is pretty much the stripes that you see here. And this like little like blinking dot is emits the heart rate, and the oximeter is kind of like what you will have on the typical Apple Watch or Garmin or any smartwatch that faces down. So I can like be the rat lab and wear it. So, and if we see here, turn it on. And the application is actually super user friendly, and again, it's aimed for meditation. So you can kind of have a guide of like you have your eyes closed and you're focused or you're not focused. It kind of has like an audio on the background that kind of helps you on that term, on that field. But the reason why these kind of started the whole topic was actually checking how reliable could be compared to an actual medical device. As you can see here, the application is like typical super user-friendly application that you see most nowadays. It has like different, like mind. So if you do a mind and like a meditation, you get like an audio and it doesn't actually show you the graph. It kind of shows you more like you're focused or distracted. So that's kind of why I dug deeper into this topic. But on the other hand, I found this other open source application that actually measures your brain waves here. So on this one, you can actually see the brain activity that is going on. And as you see, it's like all over because the eyes are open. And that's kind of what makes it less reliable. And this it really matters for the topic of the talk, because like usually when you do a study, you want to have your eyes closed, which will transition more into the typical alpha wave of the brain. So if I close my eyes, it should come down. And also if I'm not talking, but you can see that they're all over it. So after looking at this one, that's kind of what triggered the topic of digging deeper into why we can optimize this, because the way that it has been done for like forever, like 100 years, the way that it was actually written, kind of like the smographer or different aspects that you measure the movement of like the waves itself and the current. And because of that, and this is like, sorry, this is like the other application is called My Monitor, and it was inspired of a study that this device can actually be used for research. So if there's like a stimuli, and if you're looking at like different objects, if there's a kid that has like sleep apnea or different aspects, it's way easier to do this and more accessible versus actually having like a whole technician and a whole partnership with the hospital to do it. It has like this is the open source app. I think now it's like on the App Store, and I think it costs $10 now. But it used to be like fully open source. And the good thing is like you can export the data and actually have it connected to Dropbox and have like live reading right away. And with that, that kind of like brings to things to consider, like as I was mentioning earlier, the studies can vary a lot. And that's kind of what's tricky about fully automating and doing like AI or anything fancy within this topic, is because the brain and the way that it interacts, there is little different stimuli that would trigger it. For example, if I'm talking, it will be completely different because, again, since it's like a surface study, everything that is moving the scalp would not be helpful, as well as if someone has the open eyes, as we saw, doesn't help, or if there's lights. That's why, if you see a very like video full of flashes or stuff like that, there's a lot of times like a warning that could trigger seizures. I'm not sure if anyone's seen that. But that's the actual reason why, because they're like super stimulant for the brain itself. And even within the study, a lot of times there's these things intentional to measure the noise that those causes and remove them from the individual. So intentionally have something like, a click or have a light, so that when the individual sees those, we can see how that person's brain in particular react to it, so that they can remove such noise from the future, make a note of it. Also, like the reason for this one, like the tricky part is that there is not as much data for people who do not have any reason to do the study, like to put it in simple terms, like fully healthy brain. So because usually when they do it, again, it's more for like a specific disorder, like epilepsy, seizure, sleep apnea are among the most common ones. So that's kind of what trigger it, unless it's for a specific research, which is like how the brain reacts to certain stimuli. Like if they're presenting like a video, that's also very helpful to see how the person's reacting to an advertisement or stuff like that. And because of that, a lot of times they partner it with the eye stimuli. So the eye tracking. Um, so this is kind of how it looks. So as we saw, there's only like 6 lines in mine, but this is how it looks. And that's why I was going over like the structure of the brain and kind of how it's taken. So it starts from left to right. And the way the odd numbers are on the left. So that's why it starts on the left side. If you can see the notes, I'm not sure if it's visible to everyone. And this is kind of looks like more in a normal activity. I know the reason why for this is that if you know what you're looking at, sometimes it's like I'm just looking at a graph and like a line graph and I don't understand. On this case, it's more like a seizure. It's a little bit more noticeable if you compare one to another. But still, it's kind of hard to pinpoint kind of what you're looking at. You see more activity, but that doesn't mean that it's easy to process what's actually going on. And this is again has been done for like 100 years, the study itself, and it has like not changed that much. So that's why we're talking about like implementing these more with the neurology department or different aspects like that. The tricky part with this is kind of getting the people from such departments to use the technology and to because this no longer needs just the hardware. It also needs like the software knowledge a bit. Um, and again, it can be helpful for different triggers or like just seizure. So for this particular topic, again, we're focusing more on EEG. There is different ways that you can get the data. Multiple hardware and brands have their own pattern of how they compress, how they take notes. A lot of times the technician will take notes that the participant is talking or we're talking to him. So there's more stimuli. And that's why you have to keep track of those because at the end of the day, all of those would make a difference. And that's kind of why you can't fully automate it unless you have in-house person that deals with the technician and the software and the hardware. Because again, there's different versions and some of them are live. Like I can see, like you saw on the tablet, you could see immediately what's happening. Other ones kind of save it into a hard drive, like or a SD card, and then you have to copy it back and get the results from there. Um, so, and all of that makes it tricky. So that's why for this particular examples that I have is more from a 1 hour EEG that is like unstimulated. So there is no lights, no talking to make it more neutral, and as well as on a consistent location and the consistent hardware. Because for those reasons, all of those would kind of maybe slightly deviate it. So for example, in this one, we're looking already like an ICA, which is like trying to isolate the different from when you have two diodes too close to one another, what measures on the current from one to another might cannot correlate because like if it happens in between 2 points, you get the noise from one to another and to both of them. So this is already helpful to reduce the noise that happens on the overall like EEG study. And in this case, we're isolating like the E1. So if you see this one, this is like a typical linear graph, and it seems like there's noise and could be assumed that it's a seizure or different brain activity. But if you actually isolate the data on this case, it doesn't seem like that drastically different, but like without removing or filtering any external noise, just like doing the independent component analysis, we can see that now everything is more within charm. We can still see that around the 5 minutes and 45 seconds, there's still a lot of activity, but the 5:51 is now no longer considered like an outlier. And all this is already within like Python itself. The way that it's running the data, it's through the M&E library. And again, trying to make it more visual than just like the lines for the patient, no more than the doctor, because at the end of the day, the technicians and the doctors kind of like know what they're looking at and they've been trained and been looking at for a while now, especially in this study. So that's why it's for the patient, when you try to see it, sometimes it's kind of taken for granted that translation of what you're looking at. And if it is, sometimes it's like only focus on that one section. But with things like the actual M&E, we can see like in this specific section, we can only see like the brain activity more correlate to one another, but at the same time, we can see what side of the brain is coming. So we can see that it's on the right lobe, on the temporals, so it's like right and temporal. So it's easier to actually pinpoint the section of the brain that this is happening. So you don't have to necessarily understand the full graph of the lines, the linear graph, but you can also see more within different colors and actually pinpoint it and narrow it down for the patient. As well as this one, we can start seeing like a topographic example of how the head would interact on different regions. So as you see, like before, we would see like just like a spike, but it's kind of hard to understand without having the practice and knowledge of, like F15 means like frontal and 15 means it's odd, so it's on the left side and it's farther from the central line. So like without having to know all that, you can already tell what regions of the brain are getting more stimulated than others. And because of this, it's easier to do more like a follow-up. If we can see there's a consistent area that triggers the seizure, or if it's not fully clear and it's all inconsistent, there can be like a follow-up and have like an MRI that would be helpful for it. And then, like again, it's like more the different Hertz and ratio. You can like have it more only on the areas that are relevant versus having to scroll through hundreds of pages. Because if you see the linear graph is per second and you have like a 1 hour study, so you have to scroll through all those seconds of that to see the actual issues, like the trigger, sorry. And doing that as a patient is already like, you might do it for the first 10 pages, but after that you're like, okay, I see I have like this, and you just take the doctor's note without like really questioning it, or like, like trying to dig yourself more into understanding what's going on. I'm not saying to question your doctor, but also to understand yourself what's happening. So exactly, this is like the purpose of M&E. I know it's actually more actually meant for research. And there's a lot of different universities that have partnership with them, and you can use it for different regions. Like different tools. Sorry, you can use the statistical analysis and do some like, again, if you have the same patient that comes over and there's different stimuli, there's easier way to like do the statistical approach to it and narrow it down to why it gets triggered, and if there is any different reasons that, because like tricky part with seizures is that it doesn't always happen. There's like a statistical approach of, if you do it within 1 hour and the person is epileptic, it's like 25 to 50% chances that you actually spot it, which is very low compared to if you do like a 48-hour or a 24-hour. So that's why narrowing down for the patient, and if it's like a one-time seizure, is different than like multiple times. So the overall approach is to make it again more digestible, visualize how like the seizure triggers and happens within specific regions versus just seeing like a spike of lines, and understanding how that happens. Like, are there any like particular slow frequencies or things that you want to look more into it? Again, it might be worth for a tumor or an MRI follow up within it. And then again, like the actually like has like a bunch of different aspects. Again, the statistical is more when you have like a very consistent data and very consistent patients that you can get very hands dirty on like how to narrow it down and make it more fancy in the statistical aspect, which is great. But at the same time, for using it for like a one-time patient is like less applicable. And also if you're using like open source data, sometimes you don't have the notes of like how is it done? Like, is there any technician notes? Is there any eye trackment, or again, even the formatting of the hardware itself changes. So I am not sure if we have like any questions so far, kind of. Yeah, so I mean, I would say like the reason what this started is more to take advantage of like existing hardware. Because again, a lot of times like in this situation, the hardware of the EEG wasn't like the most up to date. So just because of that doesn't mean that the company or the hospital has to necessarily upgrade it immediately, because at the end of the day, it's like a measuring tool. So just because the interface might not be the most updated or the most relevant or the prettiest, doesn't mean that it's obsolete. So you can take advantage of those itself. And because of that, you can explore like this software, you just need the output of that. And because of it, we're preaching with a neuro department to actually implement it. Again, the hardest part is to get the people within the medical aspect to take the software change. And that's why a lot of times you need like people like everyone here where like, like you're on the software side, but you can help with someone that is more on the medical or hardware side of it to bridge the gap. And that's why I found this topic particularly interested. And again, it was more out of like a random yeah, like device like this one that kind of trigger it. And again, we're actually pursuing it. We had like a grant application and we applied for it, and we're like talking to connect with like neurology. So again, I'm not sure if any follow-ups or any personal look for it. Mhm. Yeah, no, thank you. So it's both kind of like what you mentioned. The second part is kind of how it's done now. As of today, usually you have, and for a lot of different like medical studies, you have the technician, the people doing the actual test, looking at it and making some notes, kind of like, oh, the brain frequency usually goes from like 0 hertz to like 100. If it goes over 100, it's definitely something going on, like not necessarily just like unnatural. So like you can pretty much disregard that because if you take out the device, if it's not measuring, that'll be an outlier. So right now the technician will make some notes, and then if there is something crazy, like the doctor will kind of have like a look, take a look of the technician note. So it's kind of like a PO, like make it easier for the doctor itself. Um, and that's kind of how it's approached most of the time. I have the software is kind of crappy, the one that they use for like the actual EEG, and it's like you can see the notes. For example, like eyes open or different aspects, or like there's like a note that says seizure, or like a brain activity or like high electrical currency. So it's actually someone looking at them manually, like the way that currently works for 90%, if not 99% of the hospitals. So that's why this is kind of trained into looking more outliers. So if you have an average, again, and that's why having the environment being consistent really matters. Even if you have like a fan noise or different aspects can affect that. So if you have this different patients, same room, same hardware, makes it easier to train the model for your specific situation. That's why for this particular reason, again, we're working for 1 hour and same location. I work with healthcare, but we're using I was using this site. So actually here I have a couple, can we all see that? Yeah, so I use OpenEuro on this one for the data. And it has like 194 data sets. I again kept it consistent. And specifically, I'm looking for epilepsy. So again, that makes it more narrowed down into, that in the data, there's gonna be like patients more likely to have epilepsy than like an average person. So that already helps it actually when training the model. Now, again, it's very unlikely to have someone do these studies without any condition or without any particular bias interest of a company trying to be like, oh, let's see how you react when you see like a Coca-Cola logo or something like that. Like that's a completely different approach that doesn't care about the other aspects of, like the study. So that's why it's kind of hard to train a model from like not be biased, because you're training the model with something that is people more prone to epilepsy or the epileptic patient. And you're also training the model for like a completely target approach. So because of that, again, that's why I feel like it's kind of hard to fully go automated from scratch. And it's very patient focused and everything you could. But again, the results you get are pretty much like just noise. And at the end of the day, kind of like it defeats the purpose of making it reliable. So that's why I was like trying to emphasize the importance of like all the different aspects. And then on that one, like you can see the summary, it's kind of like, you see more the outliers than everything. You can still see the data. Let me see if I actually finish running. You can pivot the, yeah, because you can see if I have it on this one. This one has this one has like the graph line that you can scroll through eternity of like the whole hour of by seconds. Let me see if I have it here. Sorry. I was like going over the classifiers. Oh, I'm sorry. This is actually, sorry, pause here. We can also do within stats. And again, this is more a fixed data set that I use. I did not collect the data for this one myself, but I was actually looking into the statistical approach that you can actually do within M&E as well. But yeah, so like, again, can answer your question. Currently it's manual, but the purpose of this one is exactly to try to reduce that and not take it for granted. You can still book both. And that's what I'm trying to incentivize here, when you're talking about implementing technologies like this to hospital or different aspects that, you have patients and doctors involved and, different conditions at risk. You don't want to just like, oh, like ditch everything, and like, this is a new, exactly. So exactly because of that, this is a way to kind of complement the knowledge, not fully substitute it. And at the end of the day, I feel like as of today, it's more valuable to the patient than the doctor. And that's why it's kind of hard to push the doctor to need it. Because if the doctor knows what they're looking at, they'll be looking at the same way for since they started med school, why change it all of a sudden? But as a patient, if you only do it for your first time, that's kind of why it actually matters. And here are a couple of the different websites that I kind of mentioned within my talk. Sorry. So again, this is the news. They actually have like a decent amount of research that they actually published. I like that they have here the accuracy. Like not many tracking devices have this. Like they just give like step count or heart rate, but they don't actually give you unless you really look into like the small letters of like how accurate it is. So you can see it's still not perfect by any means, like almost any hardware that is measuring would be. But at the same time, it has actually been used for different studies. So that's kind of why it led me to like more getting deeper into the device itself, and it's not just like a gadget that you get that is like for your sake only. And again, this is the application that you can see the open source data and just see it versus seeing the pretty application. This kind of gives you more the dirty graph that you can get like this one and actually do your own study. Again, only has like less electrodes. And also like another resource, sorry, and then this learning EG was great. Someone that is not fully in neurology myself, I have some knowledge from in like the department and different brain for more self-interest. Having YouTube or this website was actually very helpful because like it helps you to narrow down things like, like, oh, like the different brain frequencies, like we're mentioning, like the alpha is the typical that, when you're a person that has your eyes closed is the most common one, but that doesn't mean that it's the only one. So that's why understanding all this was needed to actually see what's going on with the graphs myself. Awesome. Anyone else has it? Mm-hmm. Mm. Mm-hmm. Yeah. No, yeah, I think for bringing it up and kind of like some of what sparked the conversation because again, the actual headband, it's like, I mean, I think the Muse 2 is more like the wireless headphones that they look like. But I mean, the Muse itself is aimed for meditation. So that's why kind of like people start using it's like, oh, you're measuring you still have electrodes and it's still attached to the brain, so you can still measure the activity. And you can have different use cases. So that's why I was like, even if the hardware is intended for something, doesn't mean that it's only meant for that. You can take advantage of the metrics and make up the most, for personal sake or for another study like that. So yeah, I have like a bunch of resources. And again, if anyone's interested, like into kind of the approach of like how we take something like a hardware like that to yourself and make up the most, like feel free to reach out. Like I had contact like actually technicians and people that work in neurology based on that. But again, I didn't want to like bore everyone like too much in depth about like how things work sometimes. And again, it was more to spark the idea of like just because something works one way doesn't mean that it's like intended to stay that way. Like and take advantage of like what exists already, like like what we mentioned. Mm-hmm. Yeah. So the question was more if I've used like machine learning to find sequence within the models, right? So I know MNE can do it. Again, since kind of mentioned that the data has to be way too consistent within the hospital and the way that the metric is done to be relevant and applicable, I don't see it as useful because you have to train very particular for a very specific department for, like imagine, the question is doing it, the way the hardware they use, the patient, the technician, making sure that it's consistent the way they do it to train the model is very particular for that specific case scenario. And the benefit that you get outside of like already kind of like getting the summaries that you already get, I don't see it as useful, at least from my perspective. That you can definitely use it within M&E, but at the same time you start adding more noise to it. And if you change locations all of a sudden, or hardware, or the way that the test is done, because sometimes they intentionally have like a flashing light to cause like a stimuli of the brain. So that itself could be triggered as a seizure if you compare it to a model that doesn't have that, because there's all of a sudden like a spike. So if you train the model using that, would kind of like also start looking for those things. So you can do it. But at the same time, I find it challenging to be fully applicable and transferable from one location to another. So if you want to do it for one and keep it consistent and do it for the future patients coming up, I think it's useful. But if you want to kind of build one model for all, I don't see the value as even though they still say it's valuable, I don't see it myself as much. Yeah. Yeah. So like kind of have the resources here. This one's there's like so many time. So yeah, like this one actually have like Nimar has like a bunch of different data sets that they have. Um like 26 terabytes of like EEG data. And this is like fully open source. Same with like on this one, they have like 194 and like over like 7,000 participants. Now, again, if you want to filter, like, they don't only have EVG. And again, this is more like EEG and epilepsy. But if you look into these ones, you already have like different data sets that, and the good thing is like they have like 30 participants, age, mostly like young participants from like 1 to 17. I guess it's more like child epilepsy in this specific case. And you can kind of take it like that. But again, I'll take it with a grain of salt because the way that the study is done does have the effect in this case. Yeah, so I mean, the hardware in this case would be like the Muse, or in the hospital if you have the actual measuring device, like the actual EEG machine, or like if you have like a Garmin, you can take the oximeter that measures your blood pressure for like not just like your heart rate, but something else. Yes. Yeah, but I mean, this is like example that is not necessarily like professional, like, and kind of what he mentioned, like, is still relatively accurate. Like that study, like he mentioned, I think 75% is like very reliable, uh, even though it's not necessarily like a professional grade. And if you saw like on the Muse, like I like that they actually published the different research that they did. So if you look into like anxiety, there's like a different studies that they actually have published themselves, not themselves, so like a university in this case. Let's see. And you can read the study and how they actually use it. And it's like those are one of the few ones that they have themselves on the website. But if you look into different studies within academia, you can find more than just these ones. Mm-hmm. Yeah. So, mm-hmm. Yeah. So I mean, the way we like to standardize the data. So you definitely could. I would say honestly, more communication within how the study gets done. Um, the one really big one that already happened like a while ago is kind of like what I showed initially. It's kind of how it gets done. It's called the 1020 system. So now I would say like most, if not all, EEG gets done by the placement of the electrodes, which is the what measures in this approach. It's called 1020 because you start on the front of the face and go at 10% and then 20% intervals, as you can kind of see on this part here on the right image. So that already standardized kind of what's placed everywhere, because if you're taking a measurement from like P4, you know where it should be and what's triggering it. So that already helps a lot. Now, kind of making the data consistent. That, again, if you're looking at different patients, sometimes you're looking about different triggers. So for example, if you have a patient that is more epileptic, again, like the blinking lights are more prone to trigger the seizure. Versus if you're looking to a patient that has like sleep apnea, like having that done in the study is kind of useless. So even though they're both doing EEGs, the intent of the study is completely different. So that's why you kind of measure differently. Now, if you're measuring both patients that are both epileptic, kind of looking to get the same, it could be more standardized. And again, the problem is like one hospital takes like longer to get the setup. And like, while it's getting set up, it's like asking the participant, it's like, oh, do you feel anything? Like, can you talk to me? Like, like, or they're talking, giving instructions, like open your eyes, look left, look right to see, again, if they have those noise. And sometimes what they do is like they trigger those noise to intentionally remove them later. So if I put a light or if I talk to you or kind of try to reduce those down the line. And also like if there's something as simple as like having like a fan, like a consistent noise that goes on and every patient would have it. It's no longer noise, but it's kind of more part of the study because it's kind of like you don't need to filter out because like everyone else has it. So you can see it still, even if you have that such noise or like that. But yeah, I mean, again, if you go to a different location, and they start talking to you more towards the end or stuff like that, that's kind of what causes more. But again, even simple things like the patient open their eyes. Like imagine they tell you have to sit down for an hour. Like maybe the patient starts to like get bored, like open the eyes to see what time is it. Like things like that is not the end of the world because like you're just opening your eyes. But again, like it definitely triggers like the different brain waves. It goes from alpha to like beta or different one. So it'd be kind of hard to make everyone behave exactly as you wanted, even though it could be simplified as like the orders that the technician gives, or the way to approach it. So again, I think like kind of going back to like the machine learning, I think it's more relevant if you do it in-house. And that's why I feel like that's the benefit of having like software knowledge and not just like the medical knowledge within even things like medical studies. Because like you don't have to be the person that is like the doctor or the technician. You can have like the bridge that kind of helps doing that between them and like also saving them time. They're going through the whole 300, like 60, 3,600 seconds and have like a shorter version of it. So again, there's value to it. And that's kind of why I actually like this topic because it kind of provides like knowledge to software that is not necessarily like programming. It's like more looking the programming with kind of more with a goal. So that's kind of why. Yeah, so the question was like how the typical data looks like. It looks like this. So this is so it's pretty much like a time series. Yeah. But this is kind of how you look. For example, if you look at this one, like the first one, it's measuring like his FP1 and F7. So it'll be the front peripheral, like number 1, and 7 is the one like so center and like on the back, so kind of like this. And it's measuring the current difference from one to another. So pretty much what it does, it's like imagining the currency, like the electrical current of one is like 2.1 and the other one's 1.9. You only measure the 0.2. So that's kind of how you're measuring this electric activity. It's kind of the difference from one diode to the other, and that's what triggers this one. And that's why if you see they're all by pairs on the left side. So it depends how long the study is. So it's usually by second, and in each second, sometimes you do like sometimes you can have like tenths of a second. So it depends how detailed it is. And again, like you can do like there is a study that's called like an ambulatory EEG, which you kind of pretty much take the device, like all the cables with you, and kind of roam around for 48 hours. So that will make it way larger than like a 1 hour study. But then again, on the second one, there's other aspects. You can expect the participant to be like at home or like at the lab doing nothing for 48 hours. So that's why usually they start with 1 hour, and if it's more needed, kind of go deeper into it. Now, it's not that heavy because you're more measuring time series, but at the same time, it depends on the length of the time that makes it heavy. And also some actually include a video of the patient so that you can tell if the patient has the eyes open, there's stimuli, he's talking, or so including the video drastically increases the actual data size. It could be helpful for training models or more in-depth analysis, but at the same time, it definitely like increases the data storage of it. Yeah, no, so that's a great point. Like actually a lot of like the noise that comes up like or like preventing from standardizing is like the stuff that happens in the background of the study that can trigger it. Like kind of like the fan or having like like the halogen light bulbs that make a noise or different aspects like that do matter. For different aspects, starting from like the actual electrical current of it. If you're measuring like um, electricity and you have like different more items that drag electricity that are not fully contained, already affected. But also the noise itself, kind of mentioning like, oh, why can you not standardize it? They try to do it as much as possible. The shorter the study it is, the easier it is. Again, 1 hour is way easier to control almost everything that you can over like a 24-hour. Because like within 1 hour, you hope that no one walks into the room that is getting the test done to ask a question. Because if you have enough signaling that like the test is getting done and please don't interrupt is needed. Now things can still happen if the patient again gets distracted or gets bored, starts moving. Again, a lot like one of the studies that we saw is like from 1 to 17 of age. So containing a kid to behave for like a whole hour, stay still is way harder because again you can't take any anesthesia or anything like that would make the person calm because at the end of the day you're also affecting the brain. So it's easier in adults, and honestly, I don't think it's that bad to standardize it within the location. But it gets tricky when you move because the way the technician approaches might change. If the technician is trying to be rushed and get it done as soon as possible and be more efficient, of course, that's one way to do it. But also, the technician is kind of like more talkative or things like that. Or, the patient is the first time they do it, might be more scared, so they might need to have more talk through it versus a person that does a regular yearly checkup. You're probably better off relying on the one yearly checkup person because they're so used to doing the study that, like it's like better and more reliable of how they're gonna react themselves to it. Um, and again, it's kind of more there is an intent of everyone doing it, especially from the medical side of it. But the big problem is like a lot of times you have first timers patients that you have to interact with, and that's kind of what triggers the inconsistency a lot of times. Thank you, everyone. Yeah, and again, if anyone has like any questions or like follow up or like personal interest, let me know. Like, feel free to reach out.